Physics of the Impossible, a scientific exploration into the world of phasers, force fields, teleportation, and time travel, by Michio Kaku. Introduction. Have you ever looked up at the stars and wondered, are we alone? Have you ever wished you could become invisible, just for a day? Or travel back in time, to witness history, or maybe even fix a mistake? What if you could walk through solid walls, or build a starship that could take you to distant galaxies faster than the speed of light? For most of us, these are the daydreams of science fiction. They are the fantasies we see in movies, the impossible tales we read in books. They are magic. But what if I told you that for one of the world's most brilliant physicists, these weren't just fantasies? What if I told you they were the starting point of a lifelong quest to understand the very limits of science? The man I'm talking about is Michio Kaku. Today, he's a world-renowned theoretical physicist, one of the pioneers of a groundbreaking idea called string theory. But his journey began not in a university lecture hall, but as a child, sitting in front of a black-and-white television, completely mesmerized by old reruns of Flash Gordon. Every Saturday, he was glued to the screen, watching rocket ships, invisibility shields, and ray guns. He didn't just see a hero saving the day, he saw a world powered by science. He realized that the real hero wasn't just Flash Gordon, but the scientist, Drive Zarkov. Without science, there was no rocket ship, no adventure, no saving the Earth. Without science, there is no science fiction. This love affair with the impossible only grew stronger. When Albert Einstein died, young Michio saw a picture in the newspaper of Einstein's desk. On it was an unfinished manuscript, the work of the greatest scientist of the age, left incomplete. He learned it was a search for a theory of everything, a single equation that could explain every force in the universe. An impossible dream. That dream lit a fire in him. He decided he would follow in Einstein's footsteps. Most kids build model airplanes. In high school, for his science fair project, Michio Kaku went to a steel company, gathered 400 pounds of scrap transformer steel, and over Christmas, he wound 22 miles of copper wire. In his mother's garage, he built his own particle accelerator, an atom smasher. His goal? To create a beam of energy powerful enough to create antimatter. This wasn't a toy, it was a 2.3 million electron-volt betatron that consumed the entire power output of his house and generated a magnetic field 20,000 times stronger than Earth's. His project won him a scholarship to Harvard, and it set him on the path to becoming the physicist he is today. In his incredible book, Physics of the Impossible, Drive, Kaku takes us on that same journey. He revisits the dreams of his childhood, the force fields, the teleportation, the time machines, but this time, he looks at them through the sharp lens of modern physics. His promise to us is simple but profound. By the end of this journey, you will no longer see the world in terms of possible and impossible. Instead, you will see it through the eyes of a physicist, and you will understand that the things we call impossible are often just waiting for the right science, the right technology, and the right minds to bring them into reality. This isn't just a book about science fiction, it's a roadmap to the future. Book summary. So, let's begin our journey into the world of the impossible. The first thing to understand is that not all impossible ideas are created equal. Michio Kaku gives us a brilliant framework for thinking about them. He divides the impossible into three distinct categories. First, there are the Class I impossibilities. These are technologies that are impossible today, but they don't violate any of the known laws of physics. They might be possible within a century, or maybe a few. Think of things like teleportation, certain forms of telepathy, and maybe even starships. Next, we have the Class II impossibilities. These are the technologies that sit right on the very edge of what we understand about the universe. If they are possible at all, it might take thousands, or even millions, of years for a civilization to achieve them. This is where we find things like time travel, hyperspace travel, and wormholes. And finally, there are the Class 3 impossibilities. These are technologies that, as far as we know, directly violate the known laws of physics. Things like perpetual motion machines that create energy from nothing. Throughout our journey today, we'll use this framework, Class 1, 2, and 3 ? As our guide. It helps us understand that when a scientist says something is impossible, they often mean it's just impossible for a civilization as young and primitive as ours. So where do we start? We start with the foundation of everything. The very forces that hold the universe together. In all of physics, we have discovered 4 fundamental forces of nature. That's it. Everything you see, everything you touch, every process in the universe, is governed by just 4 forces. The first is gravity. It's the silent force that keeps your feet on the ground and holds the galaxies together. But as a force, it's incredibly weak. Think about it. It takes the entire planet Earth, all 6 trillion kilograms of it, to pull a feather to the ground. But you can counteract that entire planet's gravity just by lifting that feather with a single finger. The second force is electromagnetism. This is the force that lights up our cities and powers our world, from radios and TVs to the internet and your phone. It can attract and repel, which is useful, but it can also be easily neutralized. A piece of plastic, for example, can pass right through a powerful magnetic field. The last 2 are the strong and weak nuclear forces. The weak force governs radioactive decay. It's what heats the center of the Earth. The strong force is what holds the nucleus of an atom together. It's the power source of the sun and all the stars. But these forces are incredibly short range. They only operate over the distance of an atomic nucleus, making them almost impossible to manipulate on a large scale. These 4 forces are the building blocks of reality. Any impossible technology must work within their rules, or find a loophole. And that brings us to our first Class I impossibility, force fields. In Star Trek, Captain Kirk's first command in a battle is always shields up. A thin, invisible barrier appears, deflecting laser blasts and enemy rockets. It seems so simple. So why don't we have them? Well, none of the 4 forces seem to fit the bill. Gravity only attracts. Electromagnetism can be easily blocked. The nuclear forces are too short range. A science fiction force field, as it's usually imagined, just doesn't seem possible with what we know. But that doesn't mean we can't create something that acts like a force field. Drive. Kaku points out a fascinating loophole, the 4th state of matter, plasma. You know about solids, liquids, and gases. But plasma, a gas of superheated, electrically charged atoms, is the most common form of visible matter in the universe. It's what stars are made of. And because it's electrically charged, you can shape it and control it with magnetic fields. In 1995, a physicist named Adi Hershkovich invented something called a plasma window. By heating a gas to thousands of degrees, he created a flat sheet of plasma, contained by a magnetic field, that could separate a vacuum from the air. When you use argon gas, it even glows with a blue light, just like the force fields in Star Trek. Now, a plasma window by itself can't stop a cannonball. But what if you created a shield made of multiple layers? Imagine this. The outer layer is a supercharged plasma window, heated to temperatures high enough to vaporize incoming projectiles. Behind that, you have a second layer, a curtain of high-energy laser beams. Thousands of crisscrossing laser beams create a lattice that would instantly heat up and vaporize anything that passes through it. And for the third layer, behind the laser curtain, you could have a screen made of carbon nanotubes. These are tiny tubes, just 1 atom thick, made of carbon. They are many times stronger than steel. If you could weave them into a lattice, you would have a screen that is invisible to the naked eye but stronger than almost any material we know. So, with a combination of a plasma window, a laser curtain, and a carbon nanotube screen, you could create an invisible wall that would be nearly impenetrable. It wouldn't be a true force field, but it would be the next best thing. There's still one problem: this shield would be transparent to a laser beam. To stop a laser, you'd need one more piece of technology: advanced photochromatics. This is the same process used in sunglasses that darken automatically when you go outside. The molecules in the glass exist in two states, one transparent and one opaque. When exposed to UV light, they instantly switch. If, using nanotechnology, we could create a material that instantly becomes opaque when hit by a powerful laser, then our multi-layered shield would be complete. It could stop bullets, rockets, and laser blasts. Developing this kind of shield is decades, maybe a century away. But it doesn't violate any laws of physics. It's a Class I impossibility. Let's move on to another fan favorite: invisibility. From Harry Potter's cloak to the cloaking device on a Klingon starship, the dream of becoming invisible is ancient. For centuries, physicists said it was impossible because it violates the laws of light. But recently, that has changed, thanks to a revolutionary new discovery: metamaterials. To understand metamaterials, we first need to understand how light works. When you put a straw in a glass of water, it looks like it's bent. This is because light slows down and changes direction when it passes from air to water. This bending is called refraction. Metamaterials are substances engineered with tiny implants inside them, things like tiny circuits or metal components, that force light to bend in ways not found in nature. Imagine a river flowing around a large boulder. Downstream, the water flows together again, as if the boulder was never there. A metamaterial could do the same thing with light. It could bend light waves completely around an object, making it seem like the object has vanished. There would be no reflection, no shadow. The object would be truly invisible. In 2006, scientists at Duke University and Imperial College in London actually built a prototype. They created a metamaterial that made an object invisible to microwaves. This was a historic breakthrough. The impossible had been achieved. But there's a catch. For a metamaterial to work, its internal structures have to be smaller than the wavelength of the radiation you're trying to bend. Microwaves have a wavelength of a few centimeters, so the implants in the first metamaterial were fairly large. But the wavelength of visible light is incredibly small, measured in nanometers, billionths of a meter. To make an invisibility cloak for visible light, you'd need to engineer a material with structures smaller than the light waves themselves. This requires nanotechnology, the ability to build things at the atomic level. The race is on. Scientists are using techniques from the computer industry, like photolithography, to etch tiny structures onto materials. In 2007, a group in Germany created the first metamaterial that worked for red light. They had achieved a negative index of refraction, something every optics textbook had said was impossible. So, what does this mean for a real invisibility cloak? It's probably not going to be a soft, flowing fabric like Harry Potter's. At least at first, it would likely be a rigid cylinder made of these metamaterials. You could hide inside it. And there's another funny problem. If you're completely invisible inside the cloak, then light can't get to your eyes, which means you'd be blind. You couldn't see out. One possible solution might be to have tiny beam splitters near the eye holes that divert a tiny, almost undetectable amount of light into your eyes. The progress here is happening incredibly fast. Within a few decades, we might have a working invisibility shield, at least for certain colors of light. It's a clear Class I impossibility. Now let's turn to the ultimate science fiction weapon: phasers and Death Stars. In Star Wars, the Death Star fires a single colossal beam of energy and completely vaporizes the planet Alderaan. A billion souls are silenced in an instant. Could such a weapon ever be real? It might be hard to believe, but there is no physical limit to the amount of energy you can cram into a light beam. The laws of physics do not forbid a Death Star. In fact, nature has already created something far more powerful: gamma-ray bursters. These are titanic explosions in deep space, second only to the Big Bang itself. They are thought to be caused by massive, dying stars collapsing into black holes. As the star collapses, it shoots out two incredibly powerful jets of radiation from its poles. If a planet were unlucky enough to be in the path of one of these jets, it would be instantly sterilized, its atmosphere stripped away, its surface scorched clean. A gamma-ray burster wouldn't just destroy life, it would erase a planet. So, the energy is possible. The challenge is harnessing it. The weapons we see in science fiction, phasers, ray guns, lightsabers, are all based on lasers. A laser works by pumping energy into a material, like a crystal or a gas, until its atoms are in an excited state. Then, a single photon of light can trigger a chain reaction, an avalanche of photons, all vibrating perfectly in unison. This creates a coherent, focused beam of light. Today, we have incredibly powerful lasers. Chemical lasers used by the military can produce millions of watts of power, enough to shoot down missiles in mid-flight. Lasers are also used in fusion research. At the National Ignition Facility in California, 192 powerful laser beams are focused onto a tiny pellet of hydrogen, creating temperatures and pressures found only in the core of a star or a hydrogen bomb. So why don't we have handheld ray guns? The problem isn't the laser, it's the power source. You would need a power pack that could deliver the energy of a massive power station, yet be small enough to fit in your palm. Right now, the only portable device that can do that is a miniature atomic bomb, which is not very practical for a sidearm. And what about a lightsaber? A glowing blade of pure energy that can cut through steel. You can't really solidify light. A beam of light doesn't just stop in midair. But you could create something that looks and acts like a lightsaber using a plasma torch. Imagine a handle that extends a thin, hollow ceramic rod. Hot, glowing plasma is pumped up through the handle and out of tiny holes along the rod. This would create a blade of superhot gas, hot enough to melt through steel. Again, the problem is the power pack. You'd either need a long cable connected to a power plant, or you'd need a breakthrough in nanotechnology to create a tiny, incredibly powerful battery. So, handheld ray guns and lightsabers are a Class I impossibility. They are possible in theory, but we need a portable power source that we just don't have yet. Maybe in the next century, with advances in nanotechnology, it could become a reality. A Death Star, however, is a different story. To destroy a planet, you'd need the energy of thousands of hydrogen bombs, all focused into a single beam. This could be done with a battery of X-ray lasers, each one powered by a nuclear explosion. A civilization that is hundreds of thousands of years more advanced than ours could certainly build such a weapon. Or, even more terrifying, they could harness the power of a dying star. By carefully controlling the collapse of a star, they could aim a gamma-ray burster at a target. A dying star could become the largest ray gun imaginable. This kind of planet-destroying technology is so far beyond our reach that drive. Kaku classifies it as a Class II impossibility. It's possible, but it would take a civilization thousands of years ahead of us. This brings us to one of the most exciting and mind-bending ideas in all of science fiction: teleportation. Beam me up, Scotty. It's a phrase that has become part of our culture. The ability to instantly transport a person from one place to another would change everything. Transportation industries would disappear. Armies could teleport behind enemy lines. We could vacation on Mars in the morning and be home for dinner. For a long time, physicists said teleportation was impossible because of the Heisenberg uncertainty principle. This is a fundamental law of quantum mechanics that says you cannot know both the precise location and the precise velocity of a particle at the same time. To teleport someone, you'd need to know the exact location of every single atom in their body, which the uncertainty principle forbids. But physicists may have been wrong. The key to real teleportation lies in a bizarre quantum phenomenon that Albert Einstein himself discovered and hated. He called it spooky action at a distance. Today, we call it quantum entanglement. Imagine you have two electrons that are created together, vibrating in perfect unison. They are entangled. Now, you separate them, sending one to the other side of the universe. According to the quantum theory, they are still connected by an invisible thread. Whatever happens to one instantly affects the other, faster than the speed of light. Let's say each electron has a property called spin, which can be either up or down. Before you measure it, the electron is in a strange state of being both up and down at the same time. But the moment you measure the electron here on Earth and find its spin is up, you instantly know that its entangled twin, on the other side of the universe, has a spin that is down. Information has traveled faster than light. Einstein thought this proved the quantum theory was wrong, but experiments have shown that it's absolutely real. You can't send a useful message this way. The information you get is random, but the connection is real. So how does this allow for teleportation? In 1993, scientists at IBM figured it out. They showed that you could use entanglement to teleport the information contained within a particle. It works like this. Let's say you want to teleport Alice, an atom, to a location where Bob, another atom, is. You start with a third atom, Charlie, which is entangled with Bob. Then, you bring Alice and Charlie together and scan them. This process transfers all of Alice's information onto Charlie. But because Charlie is entangled with Bob, that information is instantly transferred to Bob. So, Bob now becomes an exact copy of Alice. The original Alice is destroyed in the scanning process, so you don't have two copies. Her information, her very identity, has been teleported. This isn't science fiction anymore. In 1997, physicists successfully teleported a photon of light. In 2004, they teleported a whole cesium atom. In 2006, they entangled a beam of light with trillions of atoms in a gas. Progress is happening at an incredible pace. Scientists hope to teleport a complex molecule, like DNA, and maybe even a virus within a few decades. There is nothing in the laws of physics that prevents us from teleporting a human being. But the technical challenges are staggering. It takes some of the most advanced labs in the world just to entangle a few atoms. To teleport a person, you would need to scan and entangle every one of the trillions upon trillions of atoms in their body, all without losing coherence. It's a feat of engineering so vast, it might take many centuries, or even longer. So, teleporting a molecule is a Class I impossibility? We might see it in our lifetime. But teleporting Captain Kirk, that's a Class II impossibility. Possible, but a long, long way off. The technologies we've discussed so far, force fields, invisibility, phasers, and teleportation, are all on the horizon, in some form. But now we must venture further, to the very edge of our understanding of the universe. We are now entering the realm of the Class II impossibilities. And the first one we'll tackle is the dream of every space explorer, traveling faster than light. In Star Wars, Han Solo makes the jump to hyperspace, the stars stretch into long streaks of light, and the Millennium Falcon disappears into another dimension. But Einstein's theory of special relativity, from 1905, seems to forbid this. He showed that as an object approaches the speed of light, its mass increases, time slows down for it, and it shrinks in length. At the speed of light, its mass would become infinite. Time would stop, and its length would shrink to zero. This is why nothing with mass can ever reach the speed of light, let alone break it. It's the ultimate cosmic speed limit. So, is that the end of the story? Are we forever trapped in our own corner of the galaxy? Not quite. There are loopholes. Einstein himself provided the biggest one in 1915 with his general theory of relativity. General relativity describes gravity not as a force, but as the curvature of a four-dimensional fabric called spacetime. Imagine a bowling ball on a trampoline. It creates a dip in the fabric. A marble rolling nearby will be drawn into that dip, as if it's being pulled by gravity. Special relativity says you can't travel through space faster than light. But general relativity suggests that space itself can stretch and warp. And the fabric of space-time can expand faster than light. In fact, in the first fraction of a second after the Big Bang, the universe did expand much faster than the speed of light. This opens up two incredible possibilities for faster-than-light travel. The first is to stretch space. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's equations that is now called the Alcubierre drive. It's very similar to the warp drive in Star Trek. Imagine you're on a spaceship inside a warp bubble. In front of the bubble, you contract space-time. Behind the bubble, you expand it. The ship itself doesn't move at all. It just sits peacefully inside its bubble. But the bubble, and the space it contains, is moved forward by the warping of space-time around it. It would be like a surfer riding a wave. The surfer isn't moving faster than the wave, he is carried by it. You could cross the galaxy in a matter of weeks, without ever technically breaking the speed of light locally. The second possibility is to rip space. This involves creating a shortcut through space-time, a gateway that connects two distant points. We learned in school that the shortest distance between 2 points is a straight line. But that's not always true. If you take a piece of paper and fold it over, you can connect 2 points with a hole, making the distance between them almost zero. This is the idea behind a wormhole, or what Einstein called an Einstein-Rosen bridge. It's a tunnel connecting 2 different points in space, or even 2 different universes. Like Alice's looking glass, you could step through one end and instantly appear at the other, light years away. So why aren't we building warp drives and opening wormholes? There's a catch. A very big one. Both of these ideas require a form of matter and energy that is so exotic, we're not even sure it exists. They require negative matter or negative energy. Negative matter wouldn't just be light, it would be lighter than nothing. It would be repelled by gravity. If you held it in your hand and let go, it would fall up. Negative energy is a bit different. It actually exists, but only in tiny amounts. The Casimir effect, predicted in 1933 and measured in the lab, shows that 2 parallel metal plates placed very close together in a vacuum will attract each other. This is because the vacuum of space is not empty, it's fizzing with virtual particles that pop in and out of existence. These particles create a pressure. There are more particles outside the plates than between them, so they get pushed together. The energy between the plates becomes less than zero, it becomes negative energy. The problem is, you'd need a Jupiter-sized amount of negative matter or energy to open a stable, human-sized wormhole. And for the Alcubierre drive, the energy requirements are even more astronomical. So faster-than-light travel is a Class II impossibility. It's theoretically possible within Einstein's theory, but it would require a civilization that has mastered energy on a galactic scale, perhaps a Type 3 civilization. And if you can travel faster than light through a wormhole, it opens up an even more startling possibility: time travel. Time travel to the future is easy. We're all doing it, 1 second at a time. If you want to speed it up, you just need to travel near the speed of light. An astronaut who travels to a nearby star and back will find that years have passed on Earth, while they have aged only a few minutes. They have traveled into the future. But what about traveling to the past? This is where things get complicated, because it opens the door to all sorts of paradoxes. The most famous is the grandfather paradox. What if you go back in time and prevent your own grandparents from meeting? You would never be born. But if you were never born, you couldn't have gone back in time to stop them. It's a logical contradiction. Physicists have proposed 3 possible ways to resolve these paradoxes. The first is that you simply can't change the past. If you go back in time, you are forced to fulfill a role that history has already written for you. You have no free will. You might think you're changing things, but you're actually causing the events that you remember. The second possibility is that you have free will, but you are not allowed to create a paradox. Some unknown law of physics would prevent you. If you tried to shoot your own grandfather, the gun would jam, a bird would fly in the way, or you'd slip on a banana peel. The universe would conspire to protect causality. But the third, and perhaps most fascinating, resolution is the many worlds idea. This theory suggests that every time you make a decision that could change the past, the universe splits into 2. The river of time forks. In one universe, your grandfather lives. In the other, you've created a new timeline, a new parallel universe, where you were never born. This is the idea that seems most consistent with quantum mechanics. So, how could you build a time machine? A wormhole is the leading candidate. A wormhole connects 2 points in space. But because space and time are linked, it can also connect 2 points in time. Imagine you have a traversable wormhole, with 2 mouths, A and B. You keep mouth A on Earth, and you put mouth B on a spaceship and send it on a journey near the speed of light. When the spaceship returns, less time has passed for mouth B than for mouth A. So, if you step through mouth A in the year 2050, you might emerge from mouth B in the year 2030. You have traveled 20 years into the past. But again, you'd need vast amounts of negative energy to keep the wormhole open. And there are other problems. The radiation building up inside the wormhole could become infinitely powerful, destroying anyone who tries to pass through. The ultimate answer to whether time travel is possible lies in a theory of everything, a theory that unites Einstein's relativity with the quantum theory. Such a theory could tell us if negative energy can be created in large amounts, and if a wormhole would be stable enough to survive a journey. Because it sits at the very edge of our knowledge, time travel is a classic Class II impossibility. The idea of splitting timelines brings us directly to our next topic, parallel universes. This isn't just one idea, it's a collection of ideas, all emerging from the frontiers of physics. Drive. Kaku outlines 3 main types. The first type is hyperspace, or higher dimensions. We live in a world of 3 spatial dimensions: length, width, and height. But what if there are more? String theory, the leading candidate for a theory of everything, suggests that the universe might actually have 10 or 11 dimensions. The extra dimensions are just curled up, incredibly small, smaller than an atom, so we don't see them. If we could access these higher dimensions, we could perform feats that seem like magic. Imagine a 2-dimensional flatland world, like a sheet of paper. A flatlander can only see left, right, forward, and back. They have no concept of up or down. If you, a 3-dimensional being, were to float above their world, you would be invisible to them. You could reach down into their locked rooms and move things around. You could disappear and reappear at will. You would seem like a god. The second type of parallel universe is the multiverse. This idea also comes from string theory, or its more recent version, M-theory. It suggests that our entire universe is just one membrane, or brain, floating in a higher dimensional space, like a single soap bubble in a bubble bath. This cosmic bubble bath could be filled with countless other bubble universes, each with potentially different laws of physics. Some might be dead, formless collections of gas. Others might have stars and galaxies, but with forces that are too strong or too weak to allow for life. And some of these universes might even collide. A few physicists have proposed that our own Big Bang might have been the result of a big splat, a collision between two of these parallel universes. This idea is so mind-boggling, but it's consistent with some of the data we're getting from our satellites. The multiverse also offers a possible explanation for one of the biggest mysteries in science: why the constants of nature seem so perfectly fine-tuned for life to exist. If the strong nuclear force were just a little bit different, stars would either burn out too quickly or never ignite at all. If gravity were a little stronger, the universe would have collapsed back on itself long ago. It's as if the universe knew we were coming. The multiverse suggests that there are countless universes with all possible settings for these constants. Most are sterile. We just happen to live in one of the rare ones where the settings are just right. The third type of parallel universe comes from the strange world of quantum mechanics. This is the many worlds idea we encountered with time travel. The classic paradox here is Schrödinger's cat. You put a cat in a box with a radioactive atom. If the atom decays, it triggers a device that kills the cat. According to quantum mechanics, before you open the box, the atom is in a state of being both decayed and not decayed at the same time. This means the cat is both dead and alive. The many worlds interpretation says that when you open the box, the universe splits. In one universe, the cat is alive. In a parallel universe, identical in every other way, the cat is dead. Every quantum event, every possibility, branches off into its own universe. This means there is a universe where you chose a different path this morning, a universe where the dinosaurs never went extinct, a universe where Elvis is still alive. Can we travel between these universes? For the quantum universes, probably not. We have decohered from them, our wave functions no longer vibrate in unison. For the multiverse, a trip to another universe might be possible for a Type 3 civilization that can harness the Planck energy, the energy at which space and time become unstable, to punch a hole through to another bubble. Parallel universes, in all their forms, are a Class 2 impossibility. They are a logical consequence of our best and most advanced theories, but reaching them would require a technology far beyond our own. Finally, we arrive at the last category, the Class 3 impossibilities. These are things that, based on everything we know about physics, should not be possible at all. The first is the perpetual motion machine. This is the dream of a machine that can run forever, creating energy from nothing. For centuries, inventors have tried to build one. Wheels with unbalanced weights, magnets that repel each other in a circle, the designs are ingenious, but they all fail. Why? Because they violate the most fundamental laws of science, the laws of thermodynamics. The first law says that energy cannot be created or destroyed. You can't get something for nothing. This is one of the most well-tested laws in all of science. It holds true from the scale of atoms to the scale of galaxies. The second law is even more profound. It says that the total amount of disorder, or entropy, in the universe always increases. You can't even break even. Every time you use energy, some of it is lost as waste heat. A 100% efficient machine is impossible. This is why a car engine gets hot, and why your laptop needs a fan. The second law is the law of aging, of decay, of things falling apart. It's the reason it's easier to destroy something than to build it. These laws seem absolute. But there is one great mystery that could, in theory, offer a loophole: dark energy. Astronomers have discovered that the universe is not just expanding, it's accelerating. Something is pushing the galaxies apart. This mysterious anti-gravity force is called dark energy, and it makes up 73% of the entire universe. It is the energy of the vacuum itself, the energy of empty space. When we try to calculate the amount of dark energy using our current theories, we get a number that is wrong by a factor of 10 to the power of 120. That's a 1 with 120 zeros after it. It is the largest mismatch between theory and experiment in the history of science. This tells us that we are missing something huge in our understanding of the universe. If we could somehow tap into this vast reservoir of dark energy, could we power a perpetual motion machine? Probably not. The amount of dark energy here on Earth is incredibly small. But until we have a theory that can explain it, we can't be 100% certain. Because it would require overturning the most fundamental laws of physics, a perpetual motion machine is a Class 3 impossibility. The final impossibility on our list is precognition, or seeing the future. This is a power that has fascinated humanity for all of history, from the oracles of ancient Greece to the prophets of the Bible. But it directly violates one of the deepest principles of physics, causality. Cause must always come before effect. A glass shatters after it hits the floor, not before. Newton's universe was a giant clockwork machine. If you knew the position and velocity of every particle, you could, in principle, calculate the entire future. The future was determined, but you couldn't see it before it happened. Einstein's theory complicated things. It allows for closed time-like curves, which are paths that lead into the past. Time travel to the past is essentially a form of precognition. If you can know what will happen tomorrow, you can change it today. But what about receiving messages from the future? When physicists first studied Maxwell's equations for light, they found two solutions. One was a retarded wave, which travels from the past into the future. This is the light we see every day. But there was also an advanced wave, which travels from the future into the past. For 100 years, scientists just ignored this second solution. It didn't seem to make sense. Then, the brilliant physicist Richard Feynman showed what it really was. He discovered that an electron going backward in time is mathematically identical to an anti-electron, an antimatter particle, going forward in time. These waves from the future are real, but they represent antimatter. They are essential for a consistent quantum theory, but they don't allow you to send tomorrow's newspaper back to today. They don't violate causality. There is another strange idea: tachyons, hypothetical particles that always travel faster than light. They would have imaginary mass, and as they lost energy, they would speed up. It seems like you could use them to send a message to the past. But most physicists believe that if tachyons ever existed, it was only in the first instant of the Big Bang. They may have been what caused the universe to inflate, but they decayed into the ordinary particles we see today. They are no longer a part of our universe. So, seeing the future, in any meaningful way, seems to be a Class 3 impossibility. It violates causality, and any loopholes seem to be closed. For precognition to be real, our entire understanding of physics would have to be wrong. And so our journey through the impossible comes to a close. We have seen that some of the wildest dreams of science fiction may one day become the technologies of our future. We have seen that the universe is far stranger, and far more wonderful, than we could have ever imagined. Commentary. As we step back and look at the vast landscape that Michio Kaku has painted for us, one powerful idea stands out above all others: the word impossible is not a declaration of fact. It's a statement about our current level of knowledge. Think back 150 years. Some of the most brilliant scientists of the Victorian era declared that heavier-than-air flying machines were impossible. They said that building an atomic bomb was moonshine. They believed that radio had no future, and that X-rays were a hoax. In their time, they were right. The science of their day did not allow for these things. But science grows. Knowledge expands. And what was impossible yesterday becomes common sense tomorrow. Drive. Kaku reminds us that we are still a very young civilization. On a cosmic scale, we have just climbed down from the trees. We are a Type 0 civilization, still burning dead plants for energy. A Type I civilization, which has mastered all the energy of its planet, or a Type 2, which has harnessed the power of its entire star, or a Type 3, with the power of a whole galaxy, their everyday technology would seem like magic to us. This book is not just a tour of futuristic gadgets. It's a lesson in how to think. It teaches us to question our assumptions about what is and isn't possible. It encourages a sense of wonder and curiosity, but a curiosity that is grounded in the rigorous discipline of science. The most powerful lesson here, especially for someone young and ambitious, is about the nature of limits. We are all told, in one way or another, what our limits are. We are told what is practical, what is realistic, what is possible for us. But history is written by those who push past those perceived limits. So, how can you apply this grand cosmic perspective to your own life, starting today? I have 2 simple suggestions. First, pick one idea from our discussion today that truly captured your imagination. It could be invisibility, teleportation, or parallel universes. Then, just spend 30 minutes on the internet, not looking at science fiction, but looking at the real science. Search for metamaterials, or quantum entanglement, or M-theory. You will be absolutely astonished to find that the real work being done in laboratories around the world is often even stranger and more exciting than what you see in the movies. You'll begin to see the line blur between the impossible and the not yet. Second, the next time you hear someone, a teacher, a friend, or even that voice inside your own head, say that something is impossible, I want you to ask a simple question. Why? Is it impossible because it truly violates a fundamental law of nature? Or is it just impossible based on what we know right now, with the tools we have right now? That one question is the key that unlocks a different way of seeing the world. It's the difference between seeing a wall and seeing a door. Michio Kaku's journey began with a childhood love for the fantastic. But he realized that the key to unlocking the impossible was not fantasy, but physics. He devoted his life to understanding the fundamental rules of the universe, not to be limited by them, but to find out how far they could be stretched. That is the true heart of this book. It's an invitation to dream, but to dream with discipline. To imagine, but to imagine with knowledge. The future of the impossible is not written in the stars, it will be written by those who study them. That was a journey through Physics of the Impossible by Michio Kaku. We've covered a lot of ground today, from force fields to time machines, but I'll be honest with you, a summary can only take you so far. The real magic happens when you read the book for yourself. It's in the quiet moments, when a particular story or a simple phrase connects with you in a way you didn't expect. This summary is designed to help you decide if this book is worth your time. If anything we've talked about has sparked your curiosity, I truly encourage you to grab a copy. Reading it isn't just about learning cool facts, it's an experience that can genuinely change the way you see the universe and your place within it. The link to the book is in the description. Also, if you found this summary valuable, please take a moment to hit that like button and subscribe to the channel. It lets us know we're on the right track and ensures you won't miss our next journey into another life-changing book from the billionaire's bookshelf. Let's keep learning and growing together.